And we are back after momentary issues. Okay, so I wanted to give you guys another application of these identities, which I started writing down, then had to go back and fix the camera. Okay, so what if I wanted to find the sine of pi over 2? And I apologize, I already wrote some of this stuff out. I didn't feel like erasing the whole thing and then starting over from scratch. So if I wanted to find the sine of pi over 12, did I say sine of pi over 2? I meant sine of pi over 12. Sine of pi over 12. Pi over 2, but that would be easy. Sine of pi over 2 is just 1. Anyway, what I can do in order to apply this sum and difference idea is I can think about pi over 12. This is really equal to pi over 3 minus pi over 3 minus pi over 4. Right? Because I can think about pi over 3, this is really 4 pi over 12, and pi over 4 is 3 pi over 12, which is pi over 12. Now, why do I want to think of it this way? Well, the reason I want to think about it this way is because I know how to deal with trig functions at pi over 3 and at pi over 4. So if I can rewrite everything in terms of those two angles, then that's going to allow me to figure out what this is equal to. Now, so what I've done here is I've just plugged that into the sine function here, and then what we do is we apply the difference identity for sines. So we can say sine of pi over 3 minus pi over 4. That is the sine of pi over 3 times the cosine of pi over 4 minus the cosine of pi over 3 times the sine of pi over 4. Okay, so now what do we do? Well, at this point, what we can do is we can say the sine of pi over 3, remember, on your unit circle, you look around the unit circle, and the sine of pi over 3 is square root 3 divided by 2. The cosine of pi over 4 is square root 2 divided by 2. Cosine of pi over 3 is 1/2, and sine of pi over 4 is square root 2 divided by 2. So, this is going to become, let's see, everything has a square root 2 over 2. Actually, let me rewrite it this way, because there's a bunch of different ways to simplify this, and I want to kind of make it clear how we're doing it. Let me rewrite this as square root 3 times square root 2 over 4 minus 1 times square root 2 over 4. Okay, so this is kind of what I was thinking in my head, but I want to write this down before I write down the next step, so it's clear how I thought through this. And now I see I can factor out this square root 2 over 4, and I get that this becomes the square root of 3 minus 1 times the square root of 2 divided by 4. So this allows us to actually give an exact value for the sine of pi over 12. And this is really cool because remember, we had no way of figuring this out, just sort of naively trying to evaluate this function. Like we said before, it's actually really tough to evaluate functions in general, or trig functions, I should say. It's very hard to evaluate trig functions at general angles. Well, using the sum and difference identities like this really helps you out with that. So the basic rule of approach for this kind of thing, and again, there's more examples that you can see in the My Math Lab stuff and in your book, but the basic idea is if you want to evaluate sine or cosine at some angle, see if you can write it as a sum or a difference of angles that you know. If you can write it as a sum or a difference of angles that you know, then you can apply the sum and difference identities to find an exact value for what this function is going to be. Now, I should mention, of course, this only really works out if you have, angles that can be written as a sum or a difference this way. Obviously, that's not always going to be the case, but it helps us. It gets us more angles that we can get exact numbers for than we had before. Okay, so I promised that I was going to show you a different way of getting these identities. If you're not interested in seeing that, then you can feel free to turn off the video now and go practice some problems or whatever. But I do want to give you guys a bit of an extra idea here. This is Euler's identities and how they relate to the sum and difference formulas. So strictly speaking, this is a little bit beyond what we really cover in this course. I'm not going to test you on this stuff. The reason it's good to watch it anyway is because I find that this helps me remember the formulas a lot. Okay, in order to explain Euler's identities, we need to think about the function e to the I theta. Now, this looks a little bit weird. We're taking the number e, remember we talked about the number e back when we talked about exponentials, and we're raising it to I, which is the square root of -1, times some number theta. Well, what on earth is this? It turns out that using the methods of calculus, you can show that what this does is basically, as you change theta, this thing in the complex plane just traces out a unit circle. And it does so at a rate of 1. So what does that mean? Well, it means that basically the real part of this is going to be the cosine of theta, and the imaginary part, as it's called, is going to be the sine of theta. This is a result that is attributed to the mathematician, really great mathematician, discovered a lot of stuff, Leonhard Euler. And it's pronounced Euler, even though it looks like Euler, because it's a German name, and in German the EU makes the oi sound. So it's pronounced Euler, and it looks like Euler if you grew up in America learning American English, but it's Euler. So he established this, like I said, to establish this fact, really you kind of have to use some methods of calculus, because to even understand what on earth does this thing mean, you have to use some methods from calculus. But it turns out that this formula is correct. And if you accept that this formula is correct, and you also accept the usual rules for exponents still work for complex numbers. Okay, this is again a fact that is a little bit beyond what we normally do in this course, so I'm not going to establish this for you, but it turns out that this is correct. So why is this good? Well, the reason why it is good is because it makes it really, really easy to figure out these sum and difference formulas. And the reason is because I am now going to think about the following fact. If I want to find the cosine of alpha plus beta plus I times the sine of alpha plus beta, well, this would be equal to... Actually, let me write it down this way. Let's suppose that I want to do e to the I alpha plus beta, and we're just going to see what this ends up coming out to be. There are two different ways that I can think about this, okay? One way that I can think about this is what I was writing down there, but I think it makes more sense to kind of start from this direction and see what we get. So one way that I could write this down would be that this is going to be the cosine of alpha plus beta plus I times the sine of alpha plus beta. Okay, so that's what I was writing down a moment ago. I guess there was no point in erasing it and starting over, but whatever, we've already done it. The other way that I could write this down is I could use the properties of exponents. And so I could say this is actually e to the I alpha times e to the I beta. Well, what is that going to be equal to? Well, this is going to be equal to the cosine of alpha plus I sine alpha times the cosine of beta plus I sine beta. So what's going to happen here? Well, I can multiply all of these things out. And when I do that, I'm going to get cosine of alpha, cosine beta. And then when I multiply I sine alpha times I sine beta, I times I gives me a -1. So this becomes minus sine alpha sine beta. Then when I do the cross terms, I'm going to get i's in them. So then I'm going to get plus I cosine alpha times sine beta. And then I'm going to have sine alpha cosine beta. But this expression here has to equal this expression here for any values of alpha and beta. And the real part has to equal the real part. The imaginary part has to equal the imaginary part. So what we've really established is that this here is the cosine of alpha plus beta, and this over here is the sine of alpha plus beta. So in this way, using Euler's identity for writing down the imaginary exponentials in terms of trig functions, it's actually extremely fast and easy to prove these results. It almost just comes down to some very simple algebra and a little bit of properties of exponentials. Now, the hard part in doing this, of course, is using calculus to establish this identity. It turns out, fortunately, this isn't as bad as you might think. You only need to use some calculus properties about the exponential function to see that what this really is doing is it's just running around in a circle over and over again. And then you say, yeah, but the trig functions are defined to be the horizontal and the vertical components. Well, those are the real and the imaginary parts. Now, if I wanted to do the difference identities, I could do that the same way. Instead of having plus beta, I would put in a minus beta. Well, when I put in the minus beta, the only thing that's going to change is that the sign of minus beta would have the negative come out front. That's going to change some of the things that happen down here, but the same kind of argument would give me the difference identity as well. So in this way, you can use Euler's identity to very quickly establish this trig stuff. Okay, so I'm going to stop there for now. I do apologize for the really high number of technical difficulties that have been going on today. And next week, we're going to look at more applications of this stuff. We will look at identities involving tangent and, cotangent, secant, cosecant, that kind of stuff. We'll look at dealing with those kinds of things, and then we'll start looking at some other identities as well, the half angle and double angle identities, which can be even more useful for computing exact values for trig functions at various points. All right, I will see you guys then. In the meantime, don't forget to keep practicing your homework and stuff, and let me know if you guys have any questions.